The Whyline is a new debugging tool that lets programmers ask questions about their program's output and behavior. We have prototyped the Whyline in the Alice programming environment, which has been designed to help create interactive 3D simulations and animations. Alice supports a drag-and-drop interaction technique for editing code, which prevents all syntax and type errors. We'll use this Pac-Man program to demonstrate the Whyline. We'll go through 3 examples of how a programmer we'll call Ellen used the Whyline to help her implement various parts of the game. In our first example, Ellen is trying to make Pac-Man move forward like this. First, she clicks on Pac-Man in the object list and creates a new method called movePac. This will execute all of Pac-Man's animations as the program runs. She then drags a move animation to the movePac method and chooses forward 3 meters per second as parameters. She then tests her program by pressing the play button, but Pac doesn't move. Programmers typically respond to this type of failure by asking, why didn't Pac-Man move? They came up with several possible explanations. On average, it took programmers 2 to 3 minutes to diagnose this failure. With the Whyline, however, diagnosing the failure is quite simple. She clicks on the Y button, which pauses the program and brings up a hierarchical menu of why did and why didn't questions. The why did menu is generated from all of the changes to output that were executed while the program is running, and the why didn't menu is generated from all of the possible changes to output in the program, whether or not they executed. Ellen chooses why didn't Pac move forward 3 from the menu, and as she does so, the corresponding output statement is highlighted in the code editor. The Whyline's answer indicates why Pac move forward never gets executed. It says that the move statement only happens when the movePac method happens, but nothing makes movePac happen. This is an example of an invariant answer, in which some output statement always or never occurs. To fix this error, Ellen creates a new event to call movePac while the Alice program is running. She then tests the change, and Pac-Man moves as expected. In our second example, Ellen wants to make Pac-Man shrink if he touches the ghost, as shown here. To do this, she creates a do-together statement, which executes multiple statements concurrently. She puts the animation inside of it. She then adds an if statement, which checks if the ghost is within a certain distance of Pac-Man. She does this by using one of the ghost's questions, which is called is-within-threshold. She guesses that 2 meters should be about right. She then drags a resize animation, so that if Pac-Man is close enough to the ghost, Pac-Man will resize to nothing. She indicates this by choosing a resize factor of 0. When she tests the new code, Pac-Man clearly intersects the ghost, but doesn't seem to resize at all. Ellen asks, why didn't Pac-Man resize to 0? The Whyline answers by saying that Pac-Man did in fact resize, and it shows a visualization of the events that happened at runtime that caused him to do so. This is an example of a false proposition answer. The question that Ellen asked implicitly assumed that the resize did not occur, when in fact it did. Note that even though the resize did occur, she was still able to find this question in the why didn't menu. Allowing questions with false propositions allows the Whyline to reveal programmers' false assumptions about their program's execution. Ellen can drag the time cursor in order to scrub through the execution history and see that Pac-Man did in fact resize as a result of the is-within-threshold expression evaluating to true. Because the Whyline helped Ellen limit the failure to the resize statement, she decides to try a non-zero parameter. Ellen then tests this change, and Pac-Man resizes as expected. It turns out that in Alice, resizing to 0 has no effect. In our final example, Ellen wants to prevent Pac from shrinking if he's eaten the big dot, as seen here. To do this, she adds another if statement to the do-together. This will test if Pac is within 1 meter of the big dot. If this becomes true, it will set the big dot's is-showing property to false, which will cause it to disappear on screen, and indicate that it has been eaten in the code. She then elaborates the ghost collision conditional to prevent Pac-Man from resizing if the big dot has been eaten. Ellen tests the changes, but notices that even though Pac-Man obviously eats the big dot, he still resizes when he touched the ghost. Ellen simply asks, why did Pac-Man resize? In this case, the Whyline shows all of the control and data flow actions causing the resize to occur, including the if statement and the expressions evaluated as part of the if statement. As Ellen selects different events in the visualization, the code corresponding to the action is highlighted automatically in the code editor. Once Ellen notices that big dot is showing was true when the conditional was evaluated, she says to herself, wait, I saw the big dot disappear. This shouldn't have been true. She then asks, why didn't big dot is showing change to false in the context of this question? The resulting visualization combines the results of the two questions and explains that big dot is showing did change to false. Ellen traces backwards from the resize, noticing that the two conditionals were interleaved. The second conditional began to execute before the first conditional was complete. To prevent this interleaving, she stops the program and moves the big dot collision test before the do together to ensure that it gets executed before the other test does. Pac-Man becomes invincible when he eats the big dot, as expected. In user studies comparing Alice with the Whyline to Alice without the Whyline decreased debugging time by an average factor of 8 and helped programmers complete 40% more tasks than users without the Whyline in the same amount of time. We are currently investigating ways to extend the Whyline to more professional programming languages and environments, and even to desktop applications such as word processors and email clients.